fine if I don't. Can I do something else instead? Do you think this transformation can possibly be onto? Sorry, you walked in at a quiet moment. So again, I'll ask the question again. Do you think this transformation could be onto? And don't do any work. I don't want you to think. I want you to be really lazy. Bryce, sorry. I can't get it straight. I'm sorry. Oh, you're so... See, I was kind of hoping you guys would kick back and say, heck no, not possible. Yeah.
Is it not possible because continuous function, at least when applied to the transformation, would only give you a single point, or it won't give you the 4 that you need from P3?
Now, I think that ties into the answer yes. Because I'm sending from P3, I'm restricted to Paulman's degree at most 3. But when you take a peek at this other vector space, that's a vector space of all continuous functions over the entire reals. Now, do you think all polynons are continuous over the entire reals? Yeah, they are. Do you think you can give me the dimension of this vector space?
That one's 4.
Yeah, I think you could. It'd be 4. Do you think you can give me the dimension of this vector space? Probably not, because I think it would be an infinite dimensional vector space, a lot of different types of functions that are continuous, not merely the polynomials. Do you see my point? So I think it's not going to happen. And Bradley, I'm sorry, I'll answer your question now. I was just looking at it thinking I could make it more interesting. I can't answer the question. I don't remember what it was. This is number 3. Determine the kernel of the transformation. Well, I think the kernel of this transformation is going to be the collection of all polynons degree of no more than 3 whose derivatives are equal to 0. And if I'm going to transform these functions in P3 to be equal to 0, that means my second derivative function is going to be equal to 0. But if I think of that as a function in x, I think it means the first derivative function is going to be a constant. But I think it means the original function is going to be, oh, look at this, a linear function. So I think clearly the kernel of this linear transformation is merely going to be the collection of all polynomials of degree no more than 3 that are actually just linear functions. I think it's going to be nothing more than a collection of these beasts. Oh, you guys, we can be more sophisticated than this, can't we? Span of
1x.
I agree. Bradley?
Okay.
Do you disagree?
Well,
The span of x to the... I just can't hear.
Oh, I was just saying, wouldn't it be the span of x and 1, not 1 and x? It's irrelevant. It's irrelevant.
Yeah, or it's completely unimportant. Because technically speaking, that's a set. And so within a set, or is not important. Okay, you guys, your last opportunity. Anybody else? Michael?
Yeah. For number 4, for just as far as the bracket notation and stuff, how do you know you're finished, I guess, reducing all the terms when you can actually throw the span notation on?
When you remove those coefficients, like for example, just C1 and C2, when you remove those and you look at just base elements, that's when I use the span notation.
Okay.
Because I think using the SPN notation in front of the set simply means I'm looking at all linear combination of these two beasts. Oh shoot, look at that. That is what we refer to as all linear combinations of those two basic beasts and the basis of that vector space. And you know, now that you bring that up, there were a lot of issues on this exam. For example, hold on, I'm a little slow. When you take a peek at example number 6, if you're going to talk about one-to-oneness, you're probably going to take a peek at the kernel. And if you take a peek at the kernel of that linear transformation, are they going to be ordered triplets or ordered 4 tuples? Is the kernel going to contain order triplets or order 4 tuples?
It's gonna be trained, matrices.
Good, I think neither. I think neither because the kernel is supposed to be a subset of the first vector space. It's supposed to be a collection of 2 by 2 matrices. You see my point? So I saw a lot of errors with notation like that. All right, I'll stop talking. I can't think of anything else. Michael?
Actually, could you go over number 6?
Number 6. Oh, I've got too much of a mess.
Say the range should be 4 tuples or whatever.
Now, the range should be a collection of 4 tuples. I agree. Yet again, to determine if this linear transformation is indeed one-to-one, I want to take a peek at the kernel. And if I can show you, the reader, that the kernel is nothing more than a singleton set that contains a 0 element of the first vector space, then I've shown you this transformation is one-to-one. I think what that means, however, is that I've got to take the output of my transformation. That would be this mess. And set it equal to 0 element. But if I set it equal to 0 element, then equating component by component, I think that tells me that A1 plus A3 is equal to 0. And A1 minus A3 is equal to 0. It also tells me that A2 and A4 are equal to 0. And if you guys don't mind, let me just apply my math D skills to solve this system of equations. Adding both together, doesn't that give me this? And I can conclude this. Ah, shoot, you guys, with the work I have on the ink board, I've just shown you that the only thing in the kernel of my transformation is the 0 element of the first vector space. That being the case, this linear transformation is indeed one-to-one. Now, if I want to discuss onto-ness, I think the easiest thing to do is just use the general rank nullity theorem. And by the general rank nullity theorem, I think the dimension of the kernel plus the dimension of the range should be equal to the dimension of the second vector space. Yeah, I think I'm 100% completely off. And with the general rank nullity theorem, it says the dimension of the kernel plus dimension of the range really is equal to the dimension of the first vector space. I think it should be this. But that just simply tells me the dimension of the range is equal to 4. But that implies the dimension of the range. Oh, you guys, I'm getting tired of hearing my voice. Yeah, the dimension of the second vector space, which in this case is R4. But if these two spaces on the inside have the same dimension, and this one necessarily I proved to you is a subset of a subspace of the second one, that means those two vector spaces have to be the same. So I think the range of T is all for the second vector space. And by the way, now that I've shown you that I'm one-to-one and onto for this linear transformation, it necessarily implies that I've got an isomorphism, or should I say, I can create an isomorphism. Oh, actually, that's not what I asked, is it? I simply asked you to determine if T inverse exists, and find it if it does. Well, it certainly exists because I'm one-to-one and onto. But to actually find the inverse transformation, you guys check this out. With the original transformation, is it not true that the way I defined it, I took something really basic to the first vector space, told you how to create it in a complicated fashion. So I think the inverse transformation is going to pose a question, how can I take something really simplistic in the second vector space and transform it to the first vector space? What would this 2 by 2 matrix look like in terms of A's and B's and C's? That's the question. And so for me to be able to answer that question, I'm just jeepers, you guys, going to equate components. Look, A1 plus A3 is equal to A. I think A1 minus A3 is equal to B. Shoot, if if I solve a system, I suppose it tells you that A1 is equal to 1/2 the sum of A and B. Which means A sub 3 is, yikes, of A minus B over 2. Oh, I skipped something. Hold it, you guys watch. A sub 2 is equal to C. And A sub 4 is equal to D. Well, let me put it all together. I guess the output of my inverse transformation is going to be A1, A2, A3, and A4, but I've got another name for A1. Here it is. I've got another name for A2. Here it is. Another name for A sub 3 is upstairs a little bit. And lastly, another name for A sub 4 is merely my big D. I just made sure the arithmetic was pretty quick.
What did I do wrong here?
Oh, you know what? I didn't find the errors. There's a lot of arithmetic errors in there. Yeah, it just didn't match up with mine.
At this point?
Well, you can double check me.
Oh, can we go over number 3?
So number 3.
Oh.
It's not clear enough on this one.
You got 3 over 10? Oh my god, did I really? Oh, no. Because it's the magnitude squared, right? The magnitude of P1 is 10, right? Oh, Jesus. That screwed up the entire thing. Wonderful.
Yeah, Bradley, I don't think
Yeah.
I was very nice with points, only because it's taken portion.
Yeah.
Question. I apologize.
Because, I mean, it was just that one arithmetic error that just screwed up the
How
entire
many points did
thing.
it cost?
I think at least half. Can I maybe argue a couple more points since all the logic is
Oh,
correct?
you can argue. I have no problem with
Yeah.
that. Is this yours?
Yeah.
Oh, that's what I was asking earlier. Is anybody else? Any other takers? Mark?
You don't necessarily have to go through the whole thing, but I think on the third one, I was getting to where I was gonna, like, I don't know if it was me or something, but numbers just weren't coming out right. Because I checked it, and there was no clock.
It's just nothing but an arithmetic issue. That's all it really is. Are you guys clear what I meant by this, though? Because technically speaking, that means when you expand the sum out, that's going to give me an A11, B11 plus 1 plus good plus nothing. Because I think using my Dirac delta notation, delta sub 1, 1, is going to be equal to positive 1. I think I got an extra coefficient out there. Plus 2 times A1 to B1, 2. No, I'm wrong. Because these two indices are not equal to each other, that means my delta sum ij is going to be equal to 0. I think my coefficient's only 1.
Yeah. Just not bad.
All right, you finish it off. And then lastly, very nice. I agree. And you guys just got to be consistent all the way throughout using this as your definition of the inner product. And again, this portion was take-home, so I felt really comfortable doing this. And let's just crank out the first two. I will allow, I call the first one D1, just to be my first matrix. 2, 1, 1, 0 done. It's just that when it comes to D2, this is going to be my second matrix, which has these entries. But I will subtract off the projection of my D2 from my D1. I said my D2, that's not really D2, is it? It's just my B matrix. From my D1, which has entries 2, 1, 1, 0, all over the magnitude of the D sub 1, quantity squared, times my D1. You guys, I went this far. Can I just try to finish? Well, at least partially. Arithmetically speaking, let's crank a few things out. I think I've got my first matrix. Minus a fraction and let's compute this fraction. You guys watch. 1 times 2 plus 0 times 1 plus negative 1 times 1 plus 2 times 0 is a mistake. Because I gotta go back to this inner product definition. Did you guys see my point? Alright, I'll say that again. I guess what I really meant to say without a mistake is I've got a 2 times 2 plus 0 times 1 plus a negative 1 times 1 plus 2 times 0. Whereas downstairs, to compute that magnitude squared, wouldn't that just simply give me a 2 times 2 times 2? You tell me if I'm walking fast. Plus 1 times 1. Plus 1 times 1 plus 2 times 0. Oh, times a second matrix. So I guess arithmetically speaking, jeepers, you guys, I have no idea what this is. Arithmetically speaking, I guess that fraction on the outside turns out to be, is that just a 3? Over 10. And you can finish up the arithmetic. Are you guys there? Yeah, that was the easy one. That's why I'm not going to do the third one, which is so blatant with arithmetic. But like I said, I felt comfortable doing that because it was.
There's a lot of grinding.
I agree. Mark.
So when I couldn't do it that way, I started doing some Harry Potter math, and then I tried to reduce the span. Why wouldn't that work?
Reduce the span.
It obviously didn't work, but because we were given a span that it was.
Oh, I'm sorry, I see it. Right, the original set of vectors that spans the subspace.
I tried to make it a basis.
But that is a basis.
Oh, it is.
Yeah. As a matter of fact, if it were not a basis, Gram-Schmidt procedure would actually generate one of the final matrices, my D sub I, to be the zero matrix.
We'll go over number 5 in the last portion.
Oh, that was a beautiful question. I really mean that.
What? I'm confused.
Confused by what?
What you're doing.
What am I doing?
I'm not entirely sure at this point.
Well, I'm just grabbing arbitrary elements out of Rn.
Okay.
Okay, did you hear that? I don't know that this vector space is Rn. Did you guys see my point? So when I asked you to consider this linear transformation, I misspoke, didn't I? We're trying to prove it's linear. When I asked you to consider this transformation, I did not identify what that vector space was, so I didn't want you to dive into these kind of details. Do you see my point? All right, I'll backtrack. No mistakes this time. I guess what I really want to do then is grab two arbitrary elements of the first vector space. I'll call them V bar and W bar. And I think by definition this transformation just truly is nothing more than some inner product, I don't know which one, some inner product on U and the sum of these two pieces. Now if I'm trying to show that first linearity property, namely that addition breaks up, then I'd really like to break up this inner product. It's just that using my axioms of inner products, I can't do it yet. I've got to switch, commute. And if I commute, I'm left with this. Which, by the way, now allows me to come in and split this up into the sum of two values. transformation of, nothing yet. I've got to recommute. So switching one more time, I guess I've got my U-bar product with my V-bar, and then my U-bar product with my W-bar. Now I can suggest to you, the reader, that this is nothing more than V-bar transformed, and this second term over here is nothing more than W-bar transformed. I like it.
In directions it said let V be a real vector space. What did you mean by that?
Just means it's the collection of scalars are real numbers. And I didn't change the language of the author. He too all says, when we first started talking about vector space, if I talk about a real vector space, it simply means that the scalar is coming from real numbers. So you guys, if I were to verify the other linearity property, I think it's just as quick. I've got a T of added C times V bar, being nothing more than by definition of this transformation, U bar product with C V bar. I like to pull the C out, I just can't, because of that second axiom of vectors, second axiom, linear products. So let me first commute, so that I can pull out legally, and then recommute, so I can look at that transformation. I've proven the second linearity property. Now I think if you and I were to look at in V3, the description in words of the kernel's transformation, well, I think it's just simply the collection of all V bars that get transformed to 0 through this transformation. But if the output of this transformation is equal to 0 as a real number, what does that say about the relationship between V bar and U bar? They're orthogonal. And so I think the kernel in words is going to be nothing more than a plane containing all vectors orthogonal to U bar.
Real quick then, if you didn't specify, you have to specify that it's a plane containing all orthogonal vectors?
Well, yeah, notice how I was careful with my typing. I said, if V is equal to R3.
Yeah.
So I took a break and identified exactly what V was.
I just put that it's all vectors orthogonal.
And you know what, that's fine, but they've got to be orthogonal to U bar, and you said it's orthogonal to a real number.
So,
Look what you wrote. You said it's all vectors orthogonal to this piece. But this piece right here, guys, to a real number. I think you meant to say it's a collection of all vectors orthogonal to U bar. Does that satisfy what you guys? Yeah, Michael.
Could you write out?
In words, what I want to see. And maybe, Michael, I might be putting too much in here. If that first vector space really is R3, then the kernel of this transformation is the plane containing all vectors orthogonal to U bar. Now you guys need to be a little careful. I mean, what do I mean by the word orthogonal? Well, being careful, I never define what the inner product is. So it's just that relative to the inner product, I've got orthogonality. If it's our standard inner product, then you understand directly what it means.
why would it be all vectors orthogonal to U bar and not all vectors orthogonal to U bar?
Because I think the kernel's all these pieces that get sent to 0 element of the second vector space. So I really am looking at all the V bars that have this quality, and keep in mind, U bar initially was fixed. So I already fixed U bar, it's the V bars that are changing. So I guess through this transformation, all the inputs that get sent to 0 in the second vector space are all the vectors V bar orthogonal to U bar, because U bar was fixed. You guys don't look very happy. Give me some feedback now that you got the exam back. What'd you think? Was the exam fair?
It was better.
It was better.
It was better.
You know, I strongly disagree with you guys. I do insist this exam was more sophisticated, more complex than the past one. I just think you guys have, if I can say it this way, gained so much maturity with linear algebra. You're just so much stronger now.
So when's the easy exam?
The final by far is the easiest.
Are you serious?
Yeah.
Okay.
I don't believe it.
That's what Sean said in the math center, but he's like a genius, so I don't know.
It's just that by the time you get to the final exam,
He was all
you
like-
spend 6 hours each week in this classroom. You studied a lot of mathematics. You're just so
Yeah.
strong on it by the end of the
I
semester.
think he said he got like a 148 or something like that on the final, which is
Yeah,
just
I've had some pretty
insane.
large scores.
That's insane.
All right, let's let this exam go. I want to get back to solving some differential equations.
You sure we can't dwell on it?
I thought you guys are dying to get back to solving differential equations.
Differential equations.
What's that?
Do you know how much homework that we had to do?
Well, at least I'm not going to be coming in showing you that 1 + 1 is equal to 1, so that's the upside.
That was the fun part.
Yeah, actually it was.
I showed people that in the calculus club.
But
Thought it was
zero.
pretty funny, yeah.
1 + 1 = 1.
Yeah.
Does that actually work? Is that nice?
Yeah.
Don't show it to me. I'm sure my brain will quit.
1 + 1 = 1?
Yes.
You already saw it.
I don't remember saying that.
You were here that day.
I'll do whatever you like. Can you just say it a little louder?
Yeah, in class. When he showed you that?
I'm not, I guess I forgot.
Did I write it correctly?
Do you know what the quiz is going to be on Thursday? I'm just trying to, because I got so much homework for 32 I need to, and studying I need to do, so I'm trying to plan out my homework accordingly for this class, because I'm going to have to do a lot of it over the weekend.
How about if I just throw at you a really quick and easy, simple eigenvalue, eigenvector question?
Eigen? All right. And by simple and easy, you mean hard and excruciating?
No.
All right.
Okay, you guys, here's a question if you don't have your book. I want to determine all the differential operators of the form L1 and L2 such that when you look at the composition in both directions, you get the same thing. So if you guys don't mind, I'm just going to take a peek at the composition of two such linear differential operators and evaluate them y and see what the heck happens. By definition of L1, isn't that just simply this? And by definition of L2, isn't that merely this? And if I differentially operate on y through this composition, then let me just go ahead and evaluate the innermost differential operator on that unknown function y, piece of cake. This is merely going to give me b plus a1 of x. Acting on, well, let's dive into differentiate. It's not going to give me a y prime plus b1 of x times y. And now, when I differentially operate, I guess what I'm going to do is differentiate y prime once more. Oops, hold it. I meant to say y double prime. But I'm also going to differentiate the second term with respect to x. But wouldn't that give me the first? Times through the second, plus the second times through the first. Oh shoot, I forgot to push in my a sub 1 of x. Does that give me an a sub 1 of x times y prime plus a sub 1 of x b1 of x times my y? And you guys, at this stage of the game, I don't know what else you want to do. I guess I can collect my y prime terms together, my y terms together, and that's simply going to give me my y double prime, plus something times y prime, plus something times my y's. And I guess the y prime coefficients are going to be b1. I'm losing it, you guys, plus a1. Whereas the coefficients for y are simply going to be my b prime and my a1 times b1. All right, you guys, I'm happy. I think it's cleaned up as much as I can get it. I think, however, if I were to compute the composition in the other direction, acting on y, that's going to give me this reverse product. And now let me differentiate yet one more time on the inside. I think that's going to give me a y prime plus a sub 1 times y. And now differentially operating again, that's going to give me my y double prime plus, I got to slow down. Now to differentiate this product, since y is understood to be a function in x, I yet indeed do have to apply the product rule. And the product rule for differentiation says, I've got the first as is, do not touch, times the derivative of the second, plus the second times the derivative of the first. And now distributing in the multiplication process by b1 to the second two terms, that's going to give me a positive b1 times my y prime plus a1 b1y. Well, here too, you guys, just like I did in middle import, allow me to come in and just collect my y double prime terms. I'm being silly, it's only one. My two y prime terms and my two y terms. My y prime has a coefficient of, is that an a sub 1 of x? Plus a b sub 1 of x. And I think when it comes to the y coefficients, that's going to give me a sub 1 of x. Is that plus a1 b1? All right, you guys, I truly did just run amok. I wasn't very careful what I have in front of me. Now that I went through the differentiation process, let me see how I'm going to make these the same. Well, certainly my y double prime terms are already equal to each other. You know, my y prime terms are looking pretty darn clean. I think what's really causing the problem is the first term inside the set of parentheses, which, by the way, you guys check something out. I think I wrote it down correctly. Isn't that coefficient really the derivative of a sub 1 of x? And so maybe with my red pen taking a glance at what's going on here, I think the only discrepancy is here and here. So I don't know, you guys tell me, how can I make those the same? So what equal to each other? So if a1 prime and b1 prime are the same, what does that mean about a1 and b1? Good, they're not necessarily the same. Yeah, they differ by a constant. So I think clearly, according to everything I've done on the board, I can finally conclude that a1 and b1 must differ by only a constant, since their derivatives agree. What do you think? And you said you want to take a peek at 19? So use the existence and uniqueness theorem to formulate and prove a general theorem relating to the solutions to the initial value problem. A general theorem regarding the solution to the initial value problem. I'm not sure I understand what he's referring to. And the initial value problem really is the solution to this differential equation with these conditions. thoughts? Mike?
The stuff on the right, does that mean that, from y to its nth derivative, all equals 0?
Yes. In other words, the output of up to the n minus first derivative is equal to 0 some value of x that he's referring to as x of naught. And so in the end, all of these conditions right here are going to allow you to do are find the coefficients of those linearly independent solution sets to the homogeneous DE. This is a homogeneous DE because my forcing function is equal to 0. I think in the end, my solutions are going to look like this. All solutions are going to be linear combinations of n linearly independent solutions. It's just that given these n initial value conditions, it's merely going to allow me to find those coefficients C1 through Cn. And I'll be honest with you guys, I'm not sure what else he wants, other than to be able to say that I can find the values of those constants, C1 through Cn. Nothing more. Unless I'm misreading the question. I mean, I think the question was just a silly one. It's just restating what's already there. Anybody else in the homework? Yes.
Could you go over 6.2, number 35?
Number 3 is on. If you insist, but that starts my lecture today. That's exactly what I want to do.
Then we'll just go through the lecture.
All right. I don't mind.
You just do this one first.
Yes.
Oh,
Do you have a question?
yeah, actually, I think,
Yes.
6133.
So 33.
one question.
Now, you guys, I'm a little nervous about number 33 in the sense that he's the one giving me what the solution should look like. He's saying, given a differential equation of this form right here, so if I consider a solution of the DE being a function of this form, in other words, everybody, I'm being silly with my words, it's just a power function. Then what I'm going to do is I'm going to pick up this power function off the import, slap it in for y everywhere, and see what I get. Actually, do you guys mind if I walk backwards? So walking backwards, I think I have 2 times my y. But I also have 2 times x times y prime. I have my x squared times my y double prime. You guys, you just tell me if my math skills are here. Differentiating a third time and multiplying by x cubed, I suppose that gives me r times r minus 1 times r minus 2 times x to the r minus 3 power. Now the reason why those coefficients involve x cubed, x squared, x, and 1 is simply so I can now combine exponents using my basic properties or laws of exponents, and so each and every one of these terms has an x to the r power in it. Let's identify them more carefully. I think I've got an x to the r times r minus 1 times r minus 2 plus x to the r minus 1 minus 2 times r times x to the